Download this code from codegive.com, link in the description below. OK, let's delve into the world of process control blocks, PCBs, context switching, and a simplified operating system, OS, implementation focusing on a 2 to 4 process model. I'll provide a comprehensive explanation with code examples in C, a common language for OS development. Disclaimer *: this will be a simplified model to illustrate the concepts. A real-world OS is significantly more complex. This tutorial will assume a single-core CPU environment. Core concepts. 1. Process control block, PCB. The PCB is a data structure used by the operating system to store all the information needed to manage a process. It's the identity card and memory of a process from the OS's perspective. Without a PCB, the OS would have no way to track and manage individual processes. Key information stored in a PCB. * process ID, PID, a unique identifier for the process. * process state *, example ready, running, block/waiting, terminated. This tells the OS what the process is currently doing. * program counter, PC, the address of the next instruction to be executed. Crucially important for resuming execution correctly. * stack pointer, SP, points to the current top of the process's stack. Essential for managing function calls, local variables, and return addresses. * general purpose registers, the values of CPU registers, example accumulator, index registers, at the last time the process was running. * memory management information, * pointers to the process's memory regions, code, data, stack. Could be page table pointers in a virtual memory system. * priority, used by the scheduler to determine which process gets CPU time. * IO status information, information about any IO operations the process is performing, example file handles, device status. * parent PID, the PID of the process that created this process. * CPU usage, amount of CPU time used by the process. 2. Context switching, Context switching is the process of saving the state of the currently running process, its context, and restoring the state of another process. This is what allows the OS to give the illusion of multiple processes running concurrently, even on a single core CPU. Steps involved in context switching. 1. Save the context of the current process. * the OS saves the current process's CPU registers, including PC and SP, into its PCB. 2. Choose the next process to run. * the scheduler, a part of the OS, selects the next process from the ready queue based on scheduling algorithms, example round robin, priority scheduling. 3. Load the context of the next process. * the OS loads the CPU registers, including PC and SP, from the selected process's PCB. 4. Resume execution. * the CPU starts executing instructions at the address pointed to by the restored program counter. Context switching is an overhead. The OS spends time switching contexts instead of running actual application code. Therefore, minimizing context switching overhead is an important goal in OS design. 3. Simplified OS structure. We'll build a basic cooperative multitasking OS. In cooperative multitasking, processes voluntarily yield control to the OS, usually by calling a function like yield. This is simpler to implement than preemptive multitasking, where the OS can interrupt a process at any time. Components of our simplified OS. PCB array, an array to hold the PCBs for all processes. Current process pointer, a pointer to the PCB of the process currently running. Asterisk scheduler asterisk the component that determines which process runs next. In this example, we'll use a simple round-robin scheduler. Asterisk interrupt handler, simulated in a real OS, timer interrupts are used to trigger context switches in preemptive scheduling. Here, we simulate this with manual calls to yield. Asterisk process creation / termination asterisk functions to create and destroy processes. Asterisk yield, function asterisk a function that allows a process to voluntarily give up control of the CPU. 2. Code example, C. 3. Explanation and key points. 1. Data structures asterisk. Asterisk PCB, holds the process's state. Asterisk pcbs, an array of pcbs, representing all processes managed by the OS. Asterisk stacks, a 2D array to simulate separate stacks for each process. This is crucial for proper function calls and local variable management. Without separate stacks, processes would overwrite each other's data, leading to crashes and unpredictable behavior. 2. OS initialization, initialize _OS. Asterisk sets up the initial state of the OS. Marks all PCBs as unused. 3. Process creation, create _process. Asterisk finds an available PCB slot. Asterisk assigns a unique PID. Asterisk initializes the PCB fields, state, PC, SP, registers. Asterisk crucially, allocates a stack for the process by setting the SP to the top of its assigned stack region. Asterisk sets the entry point of the process. 4. Process termination, terminate _process. Asterisk marks the PCB as unused. In a real OS, this would also involve releasing any memory or resources held by the process. 5. Scheduler, schedule. Asterisk selects the next process to run based on a scheduling algorithm. Here, we use a simple round-robin approach. Asterisk calls context _switch, to switch to the selected process. 6. Context switch, context _switch. Asterisk saves the context of the current process asterisk. Asterisk saves the registers, PC, and SP into the PCB of the currently running process. This is the most critical part of context switching. It's what allows the process to be resumed later exactly where it left off. Asterisk loads the context of the next process asterisk. Asterisk loads the registers, PC, and SP from the PCB of the next process. Asterisk resumes execution asterisk. Asterisk in a real OS, this would involve setting the PC register to the restored value. In this simplified example, this is not fully achieved asterisk. 7. Yield, function asterisk. Asterisk allows a process to voluntarily relinquish control of the CPU. This is how cooperative multitasking works. 8. Example processes asterisk. Asterisk process 1 _entry, process 2 _entry, etc. These are simple functions that represent processes. They print a counter and then call yield, to give up the CPU. Asterisk the for loop inside each process simulates doing some work. 9. Main, function asterisk. Asterisk initializes the OS. Asterisk creates the processes. Asterisk starts the first process by calling schedule. 4. Limitations and improvements. 1. Simulated context switching asterisk. The most significant limitation is that the context switching is heavily simulated. A real context switch involves assembly code that directly manipulates the CPU registers and stack pointer. This example uses C variables to represent these values. 2. Cooperative multitasking asterisk. The OS relies on processes to voluntarily call yield. If a process enters an infinite loop or takes too long to execute, it can starve other processes. A real OS would use preemptive multitasking, where the OS can interrupt a process at any time using timer interrupts. 3. No memory management *. This example doesn't include any memory management. In a real OS, you would need to allocate and manage memory for each process, potentially using virtual memory techniques. 4. No I/O *. There's no handling of I/O operations, example reading from the keyboard, writing to the screen. 5. Error handling *. The error handling is very basic. A real OS would need more robust error handling to deal with unexpected situations. 6. Interrupt handling *. The interrupt handling is completely simulated. A real OS would use interrupt handlers to respond to hardware events, example timer interrupts, keyboard input. 7. No real CPU instructions *. The example does not use actual CPU instructions, it merely simulates this. V. Further exploration. Assembly language *. Learn assembly language for your target CPU architecture. This is essential for writing the actual context switching code. Preemptive multitasking *. Implement preemptive multitasking using timer interrupts. You'll need to configure a timer and write an interrupt handler that calls the scheduler. Memory management *. Study memory management techniques, such as virtual memory, paging, and segmentation. Device drivers *. Learn how to write device drivers to interact with hardware devices. Real-time operating systems, RTOS. Investigate RTOS concepts if you need to build embedded systems or applications with strict timing requirements. Let me know if you'd like to explore any of these areas in more detail. I can provide more information and code examples. Remember to compile and run the code to see the context switching in action. You can add printf statements to the functions to trace execution.